So last time we had talked about quantum numbers and how those related to atomic orbitals. Here we're going to actually talk about these specific atomic orbitals, like the s orbitals, p orbitals, and we'll talk a little bit about d orbitals and other high energy orbitals, but only very briefly, and the energies of these orbitals. So the s orbital, if we have any value for the principal quantum number, which we recall was n, value 0 is always possible for the angular momentum, which is L, and that is the S subshell. So all that means is that we can have any integer value for n, and that is a valid principal quantum number if you have an s orbital. So when L equals 0, that means the magnetic quantum number m sub L has only one value, and that's 0. So that L equals 0 is what corresponds to an s orbital. M sub L, since it's only one value, means that it can only have one orientation in three-dimensional space. Okay, so in an S subshell contains just one orbital. That's that S atomic orbital. It's spherical, which makes some sense because M sub L equals just one value. It can only have one orientation. A sphere can have only one orientation. All of the other orientations would be identical. So in that regard, that's why we have S as a spherical shape. If you increase the principal quantum number, however, that would have a different size. That would increase the size and also the energy, but it would still be spherical in its shape. When you have principal quantum number that is 2 or greater, now you have the possibility for the angular momentum, which is L, to equal 1. If L equals 1, we call that a p orbital. And there's three different orientations of a p orbital. You can have an m sub L of -1, 0, or +1 if L equals 1. And those are the three different p orbitals that we would be referring to. These different p orbitals are in an x, a y, and a z direction, and that's why they have three different atomic orbitals, three different p orbitals. These are px, py, pz, and this is what these actually look like. So the pz is along the z direction, the px is along the x direction, and the py is along the y direction. These are dumbbell-shaped orbitals. At the origin of these graphs is the nucleus. And you can see that pz is represented in two different ways. One is as these bubbles. The other one is more of that electron cloud distribution, showing that there's a very low chance that the electron is close to the nucleus. But above and below the nucleus, along that z-axis, the electrons are likely to be there. And again, remember, we talk about these atomic orbitals more so as electron clouds or probability diagrams of where those electrons are likely to be. So let's say there's a 90% chance that a particular electron in a pz orbital, let's say, would be in that location. But there would still be a 10% chance that it is outside of that location. So it's just a probability diagram of where that is likely to be. Those three p orbitals, they were the same size, shape, and therefore also the same energy, but they were just different from each other in orientation, like we had said. And that corresponds to the different m sub L's. It's not as easy as m sub L. If m sub L is -1, that's not corresponding to the pz in particular. It's actually any different one. So we can't say that the px is m sub L equals 0 and the py is +1 or anything like that. They're relatively arbitrary. So any of them are actually valid, but there are just three different orientations. Okay. And again, just with the p orbital, like the s orbital, as you increase the principal quantum number, you increase the energy and therefore the size. So that dumbbell-shaped orbital that we call a p orbital will steadily get bigger as you get a bit bigger principal quantum number. Once you get even higher principal quantum numbers, let's say 3 or greater, now 2 is a viable option for your angular momentum quantum number. And if L equals 2, then you have a d orbital subshell. These d orbitals we're not going to talk a lot about, but this is what they, there's 5 of them, so they get kind of messy. So since L equals 2, you have M sub L equaling -2, -1, 0, +1, and +2. And that would be 5 different d orbitals. And what we've been saying is d orbital orientations. It's not quite that simple. Here are the 5 d orbitals. And you can see most of them, I'd say 4 of those, are a clover shape, almost like 2 p orbitals adjacent to each other. And these just have different orientations. So if you see the, let's say the middle one there, the dxy, those dumbbells are in between the x and the y axes. But the dz squared is a bizarre one, and that is along the z-axis. The dx squared minus y squared is along the x-axis and the y-axis. So you can see that it looks a little bit different than just the orientation. There is other minor differences as you get higher and higher principal quantum numbers. So we're not too concerned about this, but these are the 5 what we're calling orientations for a d orbital. And you can imagine it gets worse. If we get one higher, you now have f orbitals, and f orbitals would then have 7 different orientations. So that gets really messy. Again, all these 3D orbitals are identical in energy. And really we're saying that there's just different orientation. You can see that it's not exactly that the case, but it primarily is. And just like the other orbitals, as you increase the energy level, you increase the size and also the energy shown for those. So 3D, 4D, 5D, as you increase that principal quantum number, you're increasing the energy of that overall orbital. Like I said, there's the f orbitals. Once you get to really large atoms, they become more important. So some locations on the periodic table we haven't talked too much about, like the very bottom of the periodic table, are the lanthanides and actinides. These are also called the F block. Those have F electrons associated with them, and that their chemistry gets pretty interesting because of this. And some elements that you're probably familiar with in the F block would be plutonium and uranium. So these are some fairly bizarre elements in general that when you get down that far on the periodic table. And these have F orbitals that, like I said, get really, really pretty messy. We're generally going to be dealing with d orbitals at the most. And even the d orbitals is that's about how far we are going to deal with in this class. Okay, so let's try one of these sample problems. Let's list the values of n, l, and m sub l for each of the orbitals in a 4D subshell. Okay, so a 4D subshell. So we're going to take a look at that. 4D gives us the values for n and l. And then we know that there's multiple possible values for m sub l because of the L. So if you take a look at 4 is our principal quantum number. So that is our n. And then D corresponds to our L. So if L equals 0, that was an S orbital. L equals 1 was a P orbital. L equals 2 was a D orbital. This is a D orbital. So we have L equals 2. So and then lastly, our m sub l is negative L to positive L, all integer values. So since L equals 2 for a d orbital, like we had said prior, m sub L can be -2, -1, 0, +1, or +2. So there are 5 different m sub L's associated with that. So there it is. You have n equals 4, L equals 2, and m sub L being those 5 different values for the 5 different orientations of a 4D orbital. This is an important note. Oftentimes, we've said that the maximum that L can be is n-1. It does not mean that L is always n-1. So here, n equals 4 but L does not equal 3. L can equal a maximum of 3, so it means that you can have a 4f orbital, but you can also have a 4d or a 4p or a 4s. So you can have L equaling 2, 1, or 0 in this, 3, 2, 1, or 0 in this case, right? And here's some energies of these orbitals. So we had talked as you increase principal quantum number, you are increasing the energy of these orbitals. But there are also some minor differences in energies between s and p orbitals and p and d orbitals, for example. But we're saying in general, at least at this point, that anything with the same principal quantum number has roughly the same energy. So the 1s is the lowest in energy. The 2s and the 2p are at very similar energies to each other because they both have a principal quantum number of 2. And those are lower in energy than the 3s, the 3p, and the 3d. And those are lower in energy, 4s, 4p, 4d, and 4f, which we're saying are all in very similar energy levels. And you can see that we are, as you go up in principal quantum number, you're accessing more subshell types. So there's no such thing as a 2d orbital, for example, or a 1d orbital. This is how this can be shown pictorially. You have this energy level, just like we had talked about previously. Those are kind of like the rungs of a ladder. So you have 1s is that lowest energy level. That was n equals 1, the principal quantum number of 1. Then you go up to the next energy level and you have 2s. And we're showing these in boxes. Each box is an orbital, and that can hold up to 2 electrons in them. One that is spin up, which was m sub s equaling plus 1/2, or spin down, which is m sub s equaling negative 1/2. And again, I should probably note that that is also arbitrary. Just traditionally, we've said up is plus 1/2 and down is minus 1/2. It does not have to actually be that case in terms of when we're adding electrons in the future. They can be added first as down or first as up. It's random. So each box is representing a total of 3 of the quantum numbers, the ones that are in Schrodinger's equation. So they exclude the one associated with the electron spin. So that's why there's only one box associated with the s orbitals, because m sub l has only one value, and that's 0, because L also equals 0. Where the 2p, however, or any p orbital, any p subshell, has 3 boxes associated with it. There are 3 different orientations. That's representing the px, the py, and the pz, for example. And then you're seeing there that the 3d and the 4d have 5 boxes associated with them, and the f would have 7 boxes associated with them. And again, we're saying that those are all on about the same energy level. So the 2s and the 2p are about the same energy level. We'll find that they're not exactly on the same energy level, but they're in the same echelon as others that have principal quantum number of 2.